Hi, everybody. Should I talk in Russia or in English? Don't say Russia. I have no clue. Yeah, I'm happy to talk here for the first time. It's the first time I'm here in Belarus, or Russia. A couple of people are still coming. So let's start slowly. For those who don't know me, I've written some books about C++. Maybe the Russian translation covers look a little bit different. Maybe not. I have no clue. And so the rough story is I'm an independent consultant, and I'm doing C++ standardization for more than 20 years. I was even involved in the first standard, but it's not my fault. Whatever you see. So, today's talk, I decided to give a little bit about a book and some new stuff I came into about C++ 17, which is out now for a couple of months and even available in some compilers. So let's talk about them. C++ 17 was standardized 1 year ago. And it's more or less a medium release. So we have a couple of minor additions. We have no big revolution. The next revolution will be C++ 20, probably bigger than C++ 11. And we will have, but we have a lot to say. I'm currently writing a book about it, covering both the language and the library. It already has 200 pages, more than 200 pages, and it's probably only half of the topics to describe, just conceptually discussing the issues there. So nothing revolutionary, many small, cool stuff, which I will talk about tomorrow in the tutorial I give. It's available already. We have it in GCC since version 7, in Clang since version 5, and in Visual Studio 2017. That's the first time we have a C++ standard already supported more or less in the same year when it was published. That was a lot worse in the past years. And we are very grateful and thankful about that. So, but there, as often, as always, I should say, in C++, there are some things that are a little bit surprising, especially if you look into the details. In this talk, I decided not to give you an overview of all the features, the cool features. Instead, I will give you tell you something about some of the new features, but I will concentrate on the surprising issues of these features. Let me say it that way, the surprises I found so far, or we found so far. So let's start with the first feature we have. The first feature we have is if with initialization. So if you have something like a lock guard, and you want to lock or protect your access to a vector v, you might use a lock guard to lock a mutex here, a mutex mv, so that we, for example, check a vector, assume v is a vector, whether it's empty, and then afterwards, if it's not empty, print the first element. That's two things. That's an initialization, and that's a check. We can do that now in one statement, and the one statement looks like this. If, then comes the initialization, then comes the semicolon, and then comes the condition. It's like an initialization in a for loop. You know it from there, and it follows the same rules. Whatever you initialize there is visible and valid until the end of the if statement, which means until the end of the else statement, if there's any. So why is there something to talk about here? Well, first of all, let me tell you some other cool stuff here, which is we not necessarily have to specify the types of function templates when we initialize them. So we can say, hey, this should be a lock guard. It's initialized by the mutex mx. Just for curiosity, I used braces here instead of parentheses. It's just that because of the initialization nightmare we have in C++, Both is possible. And now we can say, okay, the type of the lock guard is deduced, the inner type, the template parameter type is deduced by the constructor. Okay, so far so good. So somebody might come to the idea to say, why should I use a name here, like LG? Let's remove the name. So let's just create a temporary lock guard, and then we have everything locked. I don't need a name here. This is a problem because this does not create an object. The lifetime of the object created here ends immediately at the end of the initialization, not at the end of the if. So that means the effect of this way to do it would be to say, let's lock the mutex, and right after we unlocked it, we check the vector for being empty. So don't do that. Be careful with that in either way. By the way, some people like to use an underscore if they don't care for the name, but want to have a name or have to have a name. I'm not sure about this style, but this is not a style guide session. This is just a session to talk about the rules in the language. Okay, there's another issue we found in the community or in the committee, in the reflectors we discussed it. There was some early errors when using if with initialization. Here you see one example we found, or we got, that's real code from a real experience. Somebody had an if that was initializing something, and then it has an inner if, which was also then checking something. So the naive programmer said, hey, that's cool. That's an initialization and that's a condition. So let's convert it to an if with an initialization and a condition. And you are smart here as far as I heard. So you might see what the problem is. The first if is not just an initialization, it's also a condition. It's a second condition we have there. That's why we use if there. So here's missing an additional condition check, which we would have to combine with and or so. So don't be too naive. This is real code, and by the way, it resulted in a bug report because the program after this change crashed. And Jonathan Cave told us about it. Okay, next thing. Aggregates. We have new rules to deal with aggregates. In fact, what we now say is, if a data type, a structure or class, has a base class, then it can still be an aggregate, which has not been true before. So this code on the left here has a base type. A typical scenario is your base type is just a C type and you want to extend the C type. Well, this is not a C type, it uses std string, but whatever your base type does. You derive from it in a struct and add new members, maybe member functions, maybe data members. Before C++ 17, because it had a base class, this was a class. This was not an aggregate. So this has changed. This is now an aggregate. And this has some consequences. First of all, you can still create objects without initialization, having undefined values, or with curly braces having no undefined values, because even fundamental data types are initialized by 0 or false or null pointer. But and we have a new type trait, by the way, where we can check whether something is an aggregate now. Yeah, I'm sorry that the most important information is on the bottom of each slide. Okay, so, but now you can do the following. You can directly use aggregate initialization with this data type. So the way you could do it even in C already, when you had in C inner sub-objects, you could even initialize these inner sub-objects with nested braces, like here. So you pass 2 arguments to the base class, and the last argument you use to initialize your new member used. And you can skip these braces as you could always do before in aggregates, and this will still compile. And this is different from before. If we wanted to have this ability in the past, we needed a constructor that was explicitly passing the first arguments to the base class. So that's the benefit of this. So why is this an issue, or why can this be an issue? Well, there are two interesting things here. Very subtle, but they are there. The new rules are, in fact, only changed in the way that the moment you have a base class now, it can still be an aggregate, provided the base class is neither virtual nor private nor protected. So look at this example here. I have here a base class with a private default constructor, because my default constructor is only for friends of my class. So derived for another class. And the friend is my derived class. That's possible. Nothing is not possible in C++. And that's okay. This code will compile. And remember, according to the rules we have, this was no aggregate in C++ 14, but it is an aggregate now. And therefore, some different rules apply. The rule is as follows. Aggregates are not allowed to use private members of a base class or private constructors of the base class. It's not that this is a decision whether they are aggregates or not. Independent from the decision, they are not allowed to call the private members. So here you see what happens if you just declare an object of the derived class and use aggregate initialization, which is initialization using curly braces. This code did compile before C++ 17, but will no longer compile because now it falls under the new aggregate rule, which violates this. There will probably not be very much code like this, but there might be some. There's another issue in the other direction. Look at this example. This is a base, maybe a C type, and then we have a C++ derived class deriving this type. So here, for example, only adding that the default constructor is deleted. There's a little surprise. I tweeted it 1 or 2 months ago about the following fact. If you delete the default constructor and you have an aggregate, you can still create objects with empty curly braces, which is totally crazy, but it is. So remember that this was, before C++ 17, a class, but now this is an aggregate to the rules we have. So we still have an error if we try to create an object of this without any value for initialization. That should be no surprise. But due to the rule I just introduced or told you is, if you're using empty curly braces here, this will compile and initialize the values with their default values. And you could also pass a couple of values for initialization here. So we hope we fix these strange rules. There's a core working group issue which made the initial decision, which we now try to fix, because we think the moment you have a deleted default constructor, even in an aggregate, it should no longer be possible to create objects just with braces. So it should more or less maybe even not be an aggregate anymore. Next thing. I heard it even works if you don't believe. This is a nice string, but let's change it. Let's replace the first 8 characters by nothing, and let's replace the location of even, or where even is, these 4 characters of even by sometimes, and then let's find you don't, and let's replace it by I. You all know what this code does? I think it's self-explanatory. We would all probably assume this is the result, as a result, we get S with the value, it sometimes works if I believe. Note about the content of the sentence. The problem is, it's not guaranteed that this is the outcome. And that was since the beginning of C++. The outcome might also be, it sometimes works here on the belief it was, okay, you can read it yourself. Why that? Because we have no guarantee that the left side, which does a replacement of the first 8 characters by nothing, is evaluated before we try to find even. So we might first find even, then we remove the first 8 characters, and then the whole string, of course the location of even has moved to somewhere else, and it has the result you see here. This was, I would say, some surprise to some people to understand that this is the effect. And we decided to fix this. So we define a evaluation order now for some operands. So we already had evaluation order adapted from C for AND and OR, where we evaluate until the first true or first false. Now we have a defined evaluation order for some more operations. One is a dot, one is a less than and greater than expression, and a couple of more, which are typical scenarios like this. For example, if you have C out and you give out the result of F, then the result of G, and then the result of H. In the past, it was not guaranteed that F was called before G. So if the G was somehow influencing the outcome of F, it could be called first, and that could be some surprise. So we fixed that. And so the outcome here is now guaranteed, the first outcome after C++ 17, which was a real problem. We have different behavior in the compilers. Some compilers had to fix their evaluation order. So for example, look at this code. You have here a function that prints out a prefix, then an element of a vector. The index is passed as an argument, and then new line. So now let's misuse this function. Intentionally or not intentionally in practice, of course. So let's go and say, let's iterate over a vector of integers and iterate one too far. So let's iterate until the index is equal the size of the vector. And that would mean we call for each index this print element function and more for one index that is too high. So the output might be as this, as you see here. And it is on some compiler, as you see here. Look at what happens when we get the exception because of at. It might not have been happened that the prefix was printed already, because the call of at might have been called before we do the output of pre when we come to the situation. It did depend in practice on the compiler. Some were doing like that. Others were doing like what is guaranteed now. But your programs might change. If you had the output, the first output in your compiler with this example, it will change to the second output because that's guaranteed now. It's guaranteed now that the left side of the left shift operator is evaluated before we call at, and therefore before we get the exception. Okay? Let's look a little bit in the library. We have a few very cool new features and new data types. You might know them already, especially because a couple of them or many of them came from Boost. So one thing we adopted was Boost optional. Here's how you can use it now. You can say, I'm returning an int, but I might also return no int. And to save me from having a special integer value representing no int, I can say I return an optional int. So maybe not. I do this in a function that takes a string and tries to convert the string into an integer. It might work, it might not, depending on the value of the string. If the string starts with numeric digits, it will work. If not, it will throw an exception. So that's what we program here. We say we try to call string to integer, which is a standard function of C++, C++11. And we, if we get an exception, we return null opt. This has slightly changed. If you use boost, you get something different. I forgot about none opt or something like that. Or somebody knows, I'm sure. None, simply none. Ah, yeah, that's easy. Okay, so here's a loop on the bottom. In the bottom is our test case. We loop over a couple of literals. And then sometimes it works, sometimes not. So the output will be if we try to convert 42 or 077, we get an int. But if we try to convert hello, we return null opt. We check with if oi whether it's whether there's a value or not. And if not, we do something different here. Good. First of all, we had a long discussion about optional, about one problem, and that was optional of Bool. Because what happens, because you can compare an optional against the value of the underlying type. So you could say something like, if OE equals true, that was checking the value of OE against true. If you did check only if OI, then you would check whether there is a value. And that created some interesting examples, which I don't have here as a slide, unfortunately, because you could have values saying, if my value of an underlying unsigned int is less than 0, because in an optional, there's a guarantee that if there is no value is less than any other value. So there was a value less than 0 if the underlying type is unsigned in some way. The other surprise is more subtle. The other surprise, look at this. We can ask for the value in two ways. We can ask for the value with the member function value, and we can ask for the value with the member function star, or with the star operator. So, if we ask for value, and the underlying value is not there, and we use the member function value, we get an exception. If we use star, we get undefined behavior. So the second thing is probably nothing good, because you should not, if you return something optional, it might happen that there is no value, so using the value without any checking, that's probably not a good idea. Good, but look at this. Let's call getString.value and assign this to a reference. We all know that references extend the lifetime of return values, but not if something was returned by reference. And the problem is value returns the object by reference. So what you program here is that R1 and R2 refer to an object that no longer exists. They are a reference to a returned reference to an optional value that was deleted now. That will cause surprises. I'm pretty sure about it. Here's a subtle problem of that. Optional, we have optional, cool. Because I have the following problem. I have a function returning a vector of int. So let's iterate with the range-based for loop over all the returned ints. Here you see the code. For every integer I iterating over the returned vector of int returned by getVector. That's safe code. Fine. Now, let's use optional here, because I might not have a vector of int here. I might return nothing. So let's change this code as follows. Let's say I return an optional vector of int. And then what I do is, let's iterate over the returned optional of int value. The good thing is, if you return nothing, this code is safe because it throws an exception. The bad thing is if you return something, because you are now iterating over a deleted vector. And that will probably cause some trouble. So beware. We have here a general issue. That's not a new issue. I could play similar tricks with the member functions that, for example, return by reference the element of a string. Whenever you return a reference, you are in big trouble. But most of the time it works fine. But not always. So we are thinking about a new language feature. In fact, Richard Smith and me have proposed a new language feature, which will help to discover or find problems like this, so that you at least get a warning from the compiler. We only have the proposal. We are discussing whether we make something useful, something better, or whether we give a warning or error. That will be discussed. But the proposal is as follows. We propose that we can, in functions, say a return value depends on the lifetime of the object it's called for, or on a parameter or argument it is called for, so that you can specify that. And if you do that, then the compiler can find out, because the contract says, hey, your return value depends on the lifetime of the object you call this, that when the compiler deletes the underlying object, that the return value is no longer valid. So this will hopefully come. I think this is just one rough idea. If you are interested, look at paper 0936. But it will not come earlier than C++ 20, if we are lucky. That brings us to another problem. Well, before we go to another problem, let me check about timing. That's okay. So, let's talk about string view. Who here in the room has heard about string view? A couple, okay, half of the group. The idea is to say that in many cases, string is too expensive in a way that the string allocates memory for the characters. Yes, there might be a short string optimization, but in general, this is a problem, or can be a problem. So we have a type called string view, and this string view type is already used in user-defined by a lot of large code bases, because it essentially does the following. It gives you the impression you have a string, but you are not owner of the underlying memory, which is a very cool feature. Think, for example, you memory map the data from a disk into your CPU, and you don't have to copy the data, you just refer to the data with this object. Copying this object is very cheap. We can pass it by value because it does not contain any allocated memory. So, the problem I have with this is, it turns out that this community, don't mean this in the sense of sitting here in the room, I mean more, the C++ community in the world, think string view is a better string. And that's a problem. And I will tell you why. First of all, a string view does not give the same guarantees as a string gives. For example, a string view does not guarantee \0 at the end, the null terminator. As you see here, we have just an extract of a longer string here used. Second, string view might be the null pointer, which is not possible for strings. If you initialize a string with a null pointer, you have undefined behavior. If you use a default constructor, you get an empty string. For string views, if you use a default constructor and you ask for the data of the string, you get a null pointer back. And that's something you should consider if you pass the value of your string view to somewhere else, for example, to C function. So, first recommendation, always use size before using the data of a string view, because you might have to do some special checks here. The interesting thing is that in fact, string views are cheaper than strings. So if you, for example, have two functions, foo for strings and foo for a string view, if you pass a string literal, then you have to convert, in the first case, this literal to a string, allocating memory, and in the second case, you can use your string view. Funnily, there's even guaranteed to have a \0 at the end, which is a little bit strange because officially the \0 is not part of the value of a string view, but it's accidentally there. And some people already start to deal with that. So they write functions in the assumption that the passed string view comes from a literal, and that works, but that's very dangerous code. I'm not very happy about this confusion of semantics. But it gets worse. Let's first look at a positive example. Yes, we can go and say, I am not interested in a passed string that it has to have a \0 at the end. For example, I have a function, print all the elements of a collection, I pass a prefix. The prefix is a string. If I change this to taking a string view instead, note we can take the string view by value now. This works fine because we only print this string view, and the output operator of a string view knows that there might not be a \0 at the end. It does the right thing. So, and this is, by the way, this is faster. So if you pass here a string literal, you save one malloc. And then, 10 minutes only? Oh, I must be faster. Then I get, so the problem is that you're getting into trouble if you do something more. One problem you have, try to overload these functions, and you're getting ambiguities, because now both functions match. We have seen that with the hard way, so we have found a lot of issues where we said, oh, in the standard we have overloaded, for example, assignment operators taking a basic string or a string view, and we get ambiguities. For that reason, we templified some of the functions and constrained them to be available only under some conditions, and the experts of you know that this means that they have to be implemented with enable if, which is a nightmare only for library implementers, not for you. You're lucky. But we are still, all these calls are ambiguous according to the C++ 17 standard we found out in the meantime. Now it gets worse. I skip this. No, I skip this not. So you might say, okay, let's initialize a member of my class, not taking a string by reference, take a string view. That's not good, because now you have the following effect. Yes, for literal, you save a malloc. But if you pass a temporary string, this string first gets implicitly converted to a string view, and for that, it has to convert it back to a string. which then allocates memory. So you have made it worse, the usage of the constructor here, by switching to string view. Never use string views in a chain of calls if you, at the end, need a string. I told you that. So, and then there's the other thing. Never use string view as return type. We are already starting to do this in the library, by the way. Because a string view is like a pointer, as bad as a pointer, as bad lifetime issues as a pointer. Look at this. I have a function concatenating two string views. So how can I do that? We have no direct support, so let's write a function taking the two views, converting them into a string, so we get a sum string, and we return this string. Unfortunately, the result of the sum is a string, but there's an implicit conversion to a string view. A string view is a reference to the underlying data, which is the temporary return value here, which is deleted at the end of the function. You have returned a reference or a pointer to your temporary object, which is the result of this concatenation. So every code which calls concat here compiles, but results in a fatal runtime error. Now you might say, well, we can know that, okay. But it's not that easy. It's not that easy. Look at this. I write this operator makes sense, and I am smart. I say the return type is an STD string. So I'm safe now. Because I take two string views, concatenate them, the result is a string with its own memory. What could happen? Well, it could happen that somebody writes a function calling concat as a template. And this template takes two arguments of type t, and of course returns the t, because t plus t is a t. You see what happens? The problem is, if you pass a string view, then you take two string views, and there's an implicit conversion back of the return string to a string view. Bingo, we have the same problem again. Nobody has any fault here, has made anything wrong. So that's a problem. And by the way, some interesting consequences follow from this example. First of all, it's better to declare the return type as auto, not as t here. Yes, it's better. Then we wouldn't have a problem. And it's better not to declare the return type of concat to be auto. So almost always auto is broken by string view. It was anyway broken, but this was too simple. In C++, there is no simple rule for anything. So, beware of string view. Let's finally look at another library. That's a file system library. This is a file system library also adopted from Boost. We can, for example, take an argument from the command line, check whether the argument as a path exists, whether it's a regular file, whether it's a directory. If it's a directory, we can iterate over the directory, etc., etc., etc. We have two things I would like to discuss here. The one thing is, the moment we suggested to adopt the file system library to C++, I said, I want to have a function that computes a relative path between two paths. And then it started a nightmare. Because it turned out that it's totally complicated to compute the relative path between two paths. Look at this example. You have here a path, a hierarchy A, B, C, and A, D. And if you, on a Unix system, say CD, change the directory to ADE, then your shell will claim you are an ADE, but unfortunately, E is a symbolic link to AB. So you are an AB, your shell cheats. It will tell you you are an ADE, but that's not true. So from a shell, you can now say, let's go up one and go down to E. That works. But this is just part of the cheating of your shell. If you don't trust me, use CD with minus capital P or PVD with minus capital P, and you see the real location you're in when you change the directory or when you ask where am I. So we have the same problem here. We had to deal with symbolic links. So let's check two paths here, temp AX and temp AY. I changed my current path to temp. So let's check where I am. The current path is temp. And then I can say, give me the relative path from top to my directory. That's simply the absolute path without the temp. Now the interesting part comes. Let's check, how do I get from PY to PX? On the right is from, on the left is to. And of course, you have to go one up and then down to X. We have another call called relative. So we have lexical relative and we have relative, because lexically relative is not taking the file system into account. So that in other words, it ignores symbolic links. And relative is taking file systems into account. That means that lexically relative is cheaper than relative. That's an expensive call. That's not good, maybe not the best design to make the expensive call shorter than the longer, but a general pattern you see here, all cheap calls are member functions, all expensive calls are freestanding functions. So now let's create a path S, and now let's create all these files. So far this was theory. Now let's create directories there in the path, and let's create a symbolic link so that S is not a new directory under A, it's just a symbolic link to temp. And now you get the difference. So now if you ask for the lexical relative path, you go up to A and then to X, and then you go, when you ask for the relative path, the file system is taken into account and you get the other path. You should know that. Another thing I have, maybe the last thing to say, we have changed the semantics of the file system library. So if you come from Boost file system, or even if you come from TR1 or from the experimental TS file system implementation, some things have changed. So look at this program. It just takes a path, like user home nico git.git is important. And now let's use the old approach in Boost, or an experimental file system, and let's print the file name. Let's print the file name without the extension, and let's print the extension. And the interesting thing was .git was interpreted as a pure extension without having any file name. We fixed that. And we had other interesting consequences. We could iterate by calling just remove file name, and again and again we could iterate to the top. Because we could remove the file name, and by removing the file name, because we removed always the last part of the path, and we went up to this hierarchy. This code will no longer compile. It will still compile, but it will make something totally different. Because now we say, if a file name is a pure extension, nothing in front, this is not an extension, this is a file name. Which I think is a better way to say that. So that's the first fix. And the other thing is, we are no longer saying that the file name of a path that ends with a slash, with a dash, or with a separator, it has a file name. It simply has no file name, this path. So the iteration no longer works. So beware if you switch from the old experimental file system API to the new file system API, which we standardized, even if it still compiles, it will behave different. It's different namespaces, so strictly speaking, we are correct, but we have made nothing surprising, but not just replace one file system, one namespace by the other, and assume that everything works as before. That's it. I think that's it. My time is over. There are only a few things I left out. No except is now part of functions that might create some interesting effects, but that's it. That's enough for the moment. So I think that's it, and we have time for some questions about this talk. Thank you. If there's any. If there's not, I forgot one last slide, I'll just say. Because I skipped some things. Let me, before I take questions, tell you this slide. So I think C++17 is a significant improvement. We have compiler support. There are some books available. This is marketing. But I want to tell you something. This book about C++17 is written on the fly. While I write it, I already sell it, and then there will be updates for free, and there will be a special discount for all people who are here at the conference. So if you go to this website, you can get the whole book for $5. If your company pays, pay more, please. So that's it. Now, your question.
Thank you for the great talk. I have a question about if with initialization.
Yes.
If you can please switch to slide number 5.
Slide number 5.
Well, regarding the sample of code on the top of the slide, in general, I can put several variables and initialize them. And when using...
you have the same rules as in the for loop. In the for loop, you can also have multiple initialization.
So some kind of one variable or variables of a single type.
Yeah, they all have to have the same type.
Okay, thank you. And another question. On the one hand, we have string view, and on the other hand, we have interfaces like file streams, which expect in the constructors string or C string, zero terminated string. Is there any solution to use string views on such interfaces?
We are currently, well, string view came pretty late in the standardization of C++17, so it was more or less done with the last meeting. So we skipped the part that we fixed all the method that could use currently a string and now can also accept a string view, especially because of the ambiguity problem. We found some places, but we didn't fix all of them. I think the I/O streams take a string view, but for example, the regex library does not. I'm not 100% sure here. So this is a task ongoing now with C++20 that we check exactly where to adopt string view in the library.
And are the core guidelines have rules to force developers to use string views for arguments in the APIs?
My problem with string view is that we are now finding out which are useful core guidelines. We have heavy fights. We already have discussions in the standard where I say, no, this is not saying what we do. Another thing it's saying. So let's wait until somebody, I don't know, Scott Myers wakes up again and writes a book about effective C++17. So.
Okay, thank you.
Okay, thank you for the talk. Could you please switch to slide 16?
16?
Yep.
You remember all my slides? That's great.
No, I can write down things. Okay, here. Well, if I understand correctly, we already have this dispatching on ref and ref in C++ 11, right?
Yes.
So this is about doing const ref and const ref.
Yeah.
Okay, so why all of these flavors actually return references? I would expect that if you want to return value from a temporary object, then you will return.
Well, it's not
value.
necessarily a temporary. It's like the index operator of a string. Even for a constant string, we return a const character reference and not by value. So we have, that's a design issue. By reference saves you copying something. Remember, optional can have a very expensive object under the hood, and by returning it by reference, this can save you performance. So that's a design issue. The design issue is dangerous, yes. And we could have decided other way around. Maybe that's the first question for grill the committee afterwards. Why are you designing that bad interfaces?
Well, in this case, I'm not sure. Well, will this actually solve the problem that you showed on the previous slide or not?
If I can declare that the lifetime depends on the object?
Yeah, with this interface, for example.
Yes, then the compiler will detect that. Yes.
Well, how is this going to fix the problem that you showed when you return a temporary optional?
Because in the moment, if you compile this, or let's say if you compile this, then the compiler knows that that value returns a reference to an object that gets deleted, but still R1 refers to this object. And if we then use R1, we know we have made a problem.
Well, the optional itself is still going to be deleted, right?
Pardon?
The optional itself that is returned by getString will still be deleted after the semicolon.
Yes,
right?
but we will not solve. Well, we have different options how to deal with it, but we have to stop now. And the problem is we can first give a warning. That would help a lot here, or an error even.
Oh, this is about the warnings.
And the other discussion we have, if we here take this, if we have this lifetime bound of a return value to the object, we could extend the lifetime just as references do it for objects, temporary objects returned by value. But that's under discussion. So we will have a solution. It will be better if this gets accepted, whether it's only a warning, an error, or even works suddenly is something we have to discuss. And I think we have to stop now.
Thanks.
Thank you very much again. I'm here the whole evening.